In this video, we are going to solve linear systems using Cramer's rule. I think in this one, we'll probably only get through 2 by 2 matrices, and therefore 2 equations with 2 unknowns. And then I'll do a follow-up video with how to find your determinant of a 3 by 3 and to solve that way. But anyway, before we get into all that, so we're going to use Cramer's rule, and Cramer's rule uses matrices. A matrix, matrices is plural of matrix. A matrix is just a rectangular array of numbers. Now I know that sounds a little bit scary, but it just means that we're going to, kind of like a spreadsheet, we just have numbers in rows and columns. To indicate that we have a matrix, we use these square brackets. Notice that there's no separation between our lines. We just have kind of a row and columns here. We identify the size of a matrix by the number of rows, by the number of columns. So in this particular problem, we have 2 rows. So this would be row 1 and this is row 2. And we have 2 columns. This is column 1 and column 2. So we would call this a 2 by 2 matrix by putting in a little dimensions right here in the lower corner if we need to identify the size. Okay. So we are going to be solving 2 equations with 2 variables. Now we've learned in the past some techniques of looking at that. Our equations are always going to be in this form, in which you have your x's, then your y's, then your equal sign, and then your constant values on the right side of your equal sign. So the variables on one side, constants on the other side. An example of a matrix that we are going to use from this is called the coefficient matrix. Now remember, coefficients are just the numbers in front of your letters. And you'll notice that when we put it in a matrix, that we're going to just take one equation is going to represent the top row, and the second equation will represent the second row. And we get to eliminate the x's and the y's. We're just putting the numbers in, not any of the variables. So in the first row, it's my x's and then my y, so that's how I put A and then B. In the second row, it's my x coordinate first, and then my x coefficient first, and then my y coefficient in the corresponding spots. So the first column are my x coefficients, and the second column are my y coefficients. Row 1 represents the first equation here, and row 2 represents the second equation. So that's kind of how we're setting this up. Now, what are we going to do with this? Well, we're actually going to have a matrix operation. So matrices, just like anything else, we can add, subtract, and multiply most of them, depending on the size of things. There's also something out of a matrix called a determinant. The determinant is just a number that comes from a matrix. Now, more specifically, you can only get a determinant from a square matrix. So you have to have the same number of rows as columns in a square matrix. We're going to be dealing with 2 by 2 matrices. The symbol to say that we want to find a determinant, or we want to find this value, are the vertical bars. So notice how my bars no longer have the brackets on them. They're just vertical bars here instead. Okay, that is our symbol saying we want the determinant of this matrix. Now again, the determinant is just a number. We're going to calculate this number by subtracting the product of the diagonals. Ooh. So we start where we read a book up in the upper left-hand corner, and we find this first diagonal. Numbers in a diagonal, you multiply. And then we also have a diagonal going the other direction. So because those are also in a diagonal, we multiply them. But because those are going the opposite direction, we're then going to subtract those two products. And that's all we have to do to find the determinant. So in this problem here, I would be taking, it's asking for the determinant. We'd like to call it D, capital letters. The determinant is equal to, again, we don't need the D is equal to because this vertical bars is telling us that we want to find the determinant of this matrix. I'm going to say D because that's going to help us transition into our solving that we'll be doing in the next step. But to find this determinant, we start where we read a book at the -4 and multiply that diagonal first. So it's -4 times 3. Then I am subtracting the product of the diagonal going the other direction. It doesn't matter if you start at the 2 or the -1 because you're still multiplying them together. Doing your simplifying, we get -12. Now be careful here. I am subtracting, and then I'm subtracting my other product of a -2. The subtraction symbol is not the same thing as my minus sign, or of my negative number. So now I have to do my change subtraction to addition, and then change the sign after it. It was a negative, so it goes to positive. So this is -12 plus 2. If I'm -$12 in the hole and I add $2 to my account, I'm still in the hole, but not as much. So the determinant for this is at -10. So -10 is just that value. Okay? It's just a number that comes from that matrix. Okay? So the mathematics is not terribly difficult. We start where we read a book in the upper left-hand corner, have that first diagonal that direction, and subtract the product of the diagonal going the other direction. Product, remember, means multiply. The result of a multiplication is the product. Okay? So we're going to do this little math 3 times to solve a linear system that has 2 equations. But we need to make sure that we are setting it up correctly with the correct numbers inside that determinant. But the mathematics, we're just going to multiply and subtract another multiplication. Okay? So we get to do that 3 times and we can come up with our solution. But again, how do we set it up? That's the hard part. Well, it's not really that hard, but that's what the tricky part is for this problem. So here's our example. We have -3x plus 4y is equal to -22 for our first equation, and our second equation is going to be 2x plus 7y is equal to 5. Now, in order to set up our determinants, okay, I always start with the denominator. I know it looks scary because we're going to set it up as a fraction, but remember, fractions aren't really that scary if we're just simplifying a numerator and a denominator. The worst that we're going to have to do is divide at the end to simplify, or maybe reduce a fraction. So even though it looks like a fraction and those are scary, we're only reducing fractions at the end. So it's not really going to be that hard. Okay. Now you'll notice in our setups, here is our nice little setup to solve for our values. X is going to be equal to the determinant sub x, d sub x, over d, the determinant. What determinant are we talking about there? D is going to be our coefficient matrix, or the coefficient determinant. Politically correct, it's the determinant of the coefficient matrix. And notice that the bottom of both the x value and the y value have this d. Okay, now up on top, this is just a little sub value letting me know that I'm changing my x values, and this one I'm changing my y values, so it's d sub y. So to solve for x, I have to change x. To solve for y, I have to change y. What does that mean? Let's go back to the equations here. I, once again, always start with the bottom. Let me rewrite that a little bit. So, okay. And in the bottom, I'm going to put my coefficient matrix. Again, I keep the x coordinates in the first column. So my x coefficients, are -3 and 2. And the second column are the y ones, 4 and 7. in my other matrix, they're going to be exactly the same on the bottom. -3 and 2, 4 and 7. So that's why we don't have to do that matrix twice, finding that determinant, because it'll be the same value either time. Now on top, I need my d sub x. So I'm solving for x, so I'm going to replace the x coefficients. The x coefficients were the -3 and 2, and remember the x coefficients were always in that first column. So I'm going to take the -3 and the 2 out. Now what could I possibly replace it with? Well, the only numbers I have left to replace it with are the constant values. I haven't used those yet, so that goes in the first column. So I replace the x's and put the constant values in for them. The second column are the y's, and it's going to stay exactly the same. So now to calculate this, on top, we're going to take the -22 times 7 minus 4 times 5. The diagonal going in the first direction minus the diagonal going in the opposite direction. And simplify. This is -154 minus 20. They're both negative, so I get to add and keep the sign, so it's -174 is on top. Now I'm going to do the exact same mathematics on the bottom. Now this is a little trick that I do to simplify things, especially when I'm in a board like this and I have limited space, is I'm going to start this first type of step that I had up here. I'm going to write below, and then I'm actually going to work my way up instead of working down to show all of my work. So it's -3 times 7 minus 4 times 2. And then again, just showing that work or those steps, I'm going to move up instead of moving down. So -3 times 7 is a -21, minus 4 times 2 is 8. They're both negative, so again, I get to add them and keep it negative, so that's -29. So let me show it down here what I have. I have x is equal to -174 over -29. Now that looks a little bit scary, but if we actually use our calculators, it comes out to 6. What? I know, nice and easy. Okay. So now I'm going to do the same type of procedure over to find my y's. And again, I apologize that it looks a little shrunk up here. I'll work on my spacing on the next one. Here's the thing. The bottom has the same matrix, so I don't have to simplify that at all. I don't have to do that calculation. I came up with -29. It's going to be a -29 over here as well. All right, now what about the top matrix? Okay, what about that top matrix? Well, I'm solving for y, so I replace the y values. This is the other reason that I write the coefficient matrix on the bottom, because the numbers in the x column don't swap to a y, and the numbers from the y don't swap to an x. It's only the constant values that change. So I'm solving for y, so of my coefficient matrix down here, the x column stays the same. The x column is going to stay the same. It's the y values, because I'm solving for y's, I'm pulling out the y's, which are the 4 and the 7, and I once again will replace those with my constant values. So I'm solving for y, so I replace the y coefficients. The y's are the second column. So the x's were the first column, so when I was solving for x, I replaced the first column. I'm now solving for y's, so I replace the y's. And now again, it's just finding that determinant. So I have -3 3 times 5 minus negative 22 times 2. Let me write that down here maybe. So we had a negative 3 times 5 minus, and again, that minus is not the same thing as the negative on the 22, times 2. So we have negative 15. Negative and a negative will make that a positive 44. 44 minus 15 is 29. So my y is 29 over negative 29, or we would just call that y equals negative 1. Again, you can check your answers by plugging the x and the y back into the originals and showing that the left side equals the right side. I trust my math at this point, and I have no space left. So our solution is 6, negative 1. So again, coefficient matrix on the bottom. I always start with that, and then I'm solving for x, so I replace the x coefficients, which is the first column, with your constant values. To find y, again, it's the coefficient matrix, but I'm solving for y. So I replace the column that has the y's, which is the second column, with, again, the constant values. And then I find the values of my determinants. Let's do another. Since I don't have it as set up here, maybe I'll have a little bit better spacing. So again, x is going to be equal to, and I always put my coefficients on the bottom first, so it's negative 3 and 4 are my x values. The y is negative 3 and 5. I'm solving for x first, so I'm going to change the x's, which means that the y's stay the same, and the x's become the unused numbers or the constants. To solve that, we have negative 24 times the 5 minus negative 3 times 42. Let's see, this ends up being negative 120. Negative times a negative is positive. 126. 120, or negative 120 plus 126 is a positive 6. Simplifying my bottom, I'll have negative 3 times 5 minus negative 3 times 4. Start your diagonal going up, subtract the diagonal going the other way. So negative 15, negative times negative is plus 12, negative 15 plus 12, $15 in the hole, adding 12, I'm at negative 3, which simplifies to x equals negative 2. To find my y, I only change the y coefficients, so the first is still going to be negative 3 and 4. The y coefficients change to that negative 24 and 42. And on bottom, I can just write that negative 3. because it's going to be this same math right here. So now I just have to do the top math. So I have -3 times the 42 minus the -24 times 4. Let's see, that gives me a -126 again. Negative times a negative is a positive, and that's 96. -126 plus 96. I have one number that's negative, one that's positive, so I would subtract. When I learned how to subtract in 3rd grade, I would have gone 126 minus 96. The 126 is negative, so my result will be negative, and we get 30. So on top I have -30, and on the bottom I still have that -3. So simplifying that, I get y is equal to 10. Writing my solution as a point, x first, then y. -2, 10 is going to be my solution to that one. Okay. Now here's the really nice thing about Cramer's rule. So far, all of the things that we've done have come up with really pretty numbers for answers. That's not always the case in Mathland or in life. We don't always get pretty numbers as results. So I've got one more that's a little bit uglier as we work through it. So the first thing we should notice on this one is that in the first equation, we have the x's and y's on the same side of the equal sign and the constant value 4 on the other side. However, on my other equation, I have y equals 5x plus 3. And so my x's and my y's are not on the same side of the equal sign. In order to use Cramer's rule, they have to be in that form. We have to have the x's first, then your y's, then the equal sign, then the constant values. So the first thing I have to do in this problem is subtract the 5x to the other side. Now I can't combine a 5x with a y because they're not like terms, and I need to put the 5x first. So this equation now ends up being -5x plus y is equal to 3. Other equation stays as it is. Come on. 6x. Okay. 6x minus 2y equals 4. Again, now I'm now solving for my x first. X is equal to, and I like to fill in my coefficient matrix first on the bottom. 6, -5, -2. Now it doesn't look like there's a number in front of the y. Remember, 1 is always there. The God of Mathland is there whether we see him, her, it, or not. And then on top, I replace those first, because I'm solving for x, so I replace the x values with the 4 and the 3. And I have the -2 and the 1 in the second. All right, so the second column stays exactly the same. It's the first column that switches. Start where we read a book in the upper left-hand corner. Find your diagonal going down, multiply that. So it's 4 times 1. Then we're always subtracting because the next diagonal is going the other direction. Diagonal is going the opposite direction. We subtract. So we end up with 4 plus 6, or 10 on top. On the bottom, it's the same thing. 6 times 1. Then the next diagonal is going the opposite direction, so I'm subtracting. -2 times the -5. So I get 6, negative, negative, negative. Odd number of negatives will be negative, So 6 minus 10 is a negative 4. So now we have one that doesn't simplify very nicely. But we can still reduce this fraction. We can't take 10 divided by a negative 4 and get a pretty number, but we can reduce it. 2 goes into both of those numbers evenly. So we would get x is equal to negative 5 over 2. Now, next, x equals negative 5 over 2. Notice I put the negative on the top because I prefer my negatives on top, so it makes more sense to me. And we just leave it like that. It's okay to have that as your x value. Now when we find y, again, I don't have to substitute in this ugly fraction to find y. I can find y using my Cramer's rule instead. Remember, on top, the x coordinates now, or the x coefficients, that first column will stay the same, and it's the second column that changes from the negative 2, 1 to the 4, 3. The denominator will still be that coefficient matrix, which was that negative 4 that we came up with here. So again, now I just have to simplify doing the top. Value of that determinant, start on the upper corner, 6 times 3, and then subtract the diagonal going the other direction, which is 4 times negative 5. 18 minus a negative, so I'm adding 20. So I get 38 for my top number. So I end up with 38 over a negative 4. Again, kind of scary, but not too bad, because I just have to reduce. Divide both of them by 2, you end up with negative 19 over 2. Again, a negative either goes on the top or the bottom, but not both. I don't like it on the bottom, so I stick it up on top so I don't lose it. So that's my y value. So my solution to this one is negative 5 halves and negative 19 halves. Okay. So even though we ended up with scary, ugly numbers, it wasn't too hard to get that. I didn't have to deal anything with the fractions. They just showed up at the end that I just had to reduce. I didn't have to do anything else with it to deal with those ugly answers. Now, it's not to say that you're going to get too many that are going to have any ugly answers. Again, most of the problems that we are going to deal with, since you are just first learning this procedure, is going to have pretty numbers. But if they happen to be a little bit uglier, halves or quarters or something of that sort, it's really not going to be terribly difficult to get those answers. Other methods, like substitution or elimination, it would be a little bit more difficult to deal with those fractions. So that's the bonus about Cramer's rule. Now in our next video, we're going to find out how to find the values of the determinants of a 3 by 3 matrix. Remember, determinants you can only find from square matrices, so they have to have the same number of rows as columns. And then we're going to use that to solve a system that has 3 variables and 3 equations. So again, we're actually going to do the exact same procedure as we did here. We're going to find x by taking the determinant with replacing the x values over the coefficient determinant, the matrix of that. Y is going to be found by taking the determinant when we change the y column over the coefficient matrix. And z is going to be the determinant of the matrix when we replace the z column all over the coefficient matrix. However, calculating the determinant of a 3 by 3 is a little bit more involved than what we just had to do here with the 2 diagonals. So we'll practice that on our next video.